Okay, option A is an option that covers the analysis of chemical compounds. It's titled Analytical, well, the whole section is called Modern Analytical Techniques. And what we're going to learn is we're going to learn, I believe, 4 different techniques for analyzing chemical compounds. Now, this first category basically has 2 points for you to know. The first is the reasons for using these techniques. Well, there's your answer. You can read that on your own. Basically, to determine the structure, to determine the presence of a chemical, or to determine its purity, how much of it, like percentage in a sample. Very simple. You can read that on your own. This is an important one here. This point here. This states that the compound itself, one technique by itself is not enough. You're going to need a combination of these techniques to determine the structure. And so to go through them, and I hope I cover them all by memory here. This is in no particular order. And we're going to cover these the next few pages will have these expanded upon. The first is called infrared spectroscopy. That's what the IR stands for, infrared. So in infrared spectroscopy, we are investigating, excuse me, that was strange. What functional groups are present? What functional groups are present. Another one we're going to learn is called hydrogen nuclear magnetic resonance. It's going to detect or determine locations of hydrogens. It'll be self-explanatory once we get to that particular process. Let me get this out of the way. We're going to learn mass spectroscopy. Which will help us to determine primarily molar mass as its real function. It does help us determine what functional groups a little bit, but its primary use is for determining molar mass. And there are 2 other techniques that we can kind of throw in here. I'm going to lump them into one big thing. That is atomic absorption and chromatography. Now the first 3 we're really going to hit hard. They're going to help us discuss the structure, mass, arrangement of the functional groups in the compound. These down here are more of a after thing. As a matter of fact, you guys have done this here, atomic absorption. You've either done it in chem or you've done it in bio. This is where you use Beer's law or the Beer-Lambert law, and maybe the Bradford test for those of you in bio. We probably did something in pre-IB. I don't think we did it this year. Yeah, we did. We used the spectrophotometers this year, didn't we? So it'll be related to spectrophotometers, Beer's law, Bradford test. So that'll make more sense as we move along. So let's go ahead and get through. The first thing we need to understand is how we can. Let me make these a little bigger for you guys. Is how we use the electromagnetic spectrum to perform these tests. Because if you we're thinking clearly, infrared spectroscopy uses a type of light. Atomic absorption will use a type of light. And you could argue that nuclear magnetic resonance uses a specific type of light. However, it won't really be that important for us to know. So just wanted to let you guys know that various types of light. We have the visible range. So we'll put that in the center. And we'll make a little spectrum here. In our spectrum, we'll have that. We'll have 3 terms on the spectrum. We'll have energy, we'll have wavelength, and we'll have frequency. So remember that types of light that are, let's say, higher in energy, so I'll put high here to indicate energy increasing. Those types of light are things like ultraviolet, X-ray, gamma rays, just as a reminder. And lower energy types of light are infrared, radio, microwaves would be down there. It's not super important that you know all the types, so this would be lower energy. Now remember the relationships here. The relationship between energy and energy and frequency is this. That is direct. And the relationship between wavelength and frequency is this, that is inverse or indirect. So if we apply that reasoning up here, since frequency and energy are direct, this would be increasing frequency, this would be decreasing frequency, and this is inverse, so the wavelengths at the frequency gets high, this gets lower, or shorter, I guess is a better way, and this gets higher or longer. Hopefully you guys remembered all that stuff. So you just need to be able to understand the parts of the electromagnetic spectrum, so it can talk about, they'll ask you questions about types of light. Just make sure you understand that. This point down here is referring to absorption and emission. So the word says it all. The word absorption basically means how much energy is absorbed, and emission is how much is released. Now this is specific, this discussion is specific to the structure of the atom. So if I have some chemical, we'll just call it chemical X. If this chemical has, this chemical does have electrons which are in energy levels. So remember, if we focus on an electron on the first energy level, if we bombard this with a certain type of electromagnetic radiation, remember that radiation has a certain frequency, a certain wavelength, or a certain energy. We could report it to you in any one of those, using any one of those terms. Well, that electron may absorb that energy if it's sufficient, and it may climb to a higher energy level. So we can symbolize it climbing up from the first to the third. Now, if we were to chart, if we were to measure or use a machine that could measure the amount of light emitted from this, say there's a light bulb and this is our source of electromagnetic radiation. If we knew how much electromagnetic radiation was entering into the sample, if we then compared the amount that got through to what was shined or passed through the sample, that's how we could detect absorption. It's basically how much was removed. That's what the word gives it away. In some cases, electromagnetic radiation, as I was alluding to, this electron would absorb it, and that electron would then release that stored energy, and it could either fall all the way back to its original location, or of course it could do it in steps. There's so many atoms in the sample, both or all possibilities in that sense would occur. Well, each time it fell back down, it would be releasing photons of particular wavelengths. So I'm putting E for energy, but please understand that each of those transition produces a photon of a different frequency. I used 2 twice, sorry. And therefore, because each of those has a different frequency, we would detect a different type of light. That is emission, an emission spectrum. Absorption is what is taken out of the original sample. Emission is what it emits after it absorbs something. So you could say that if the absorption, the amount that passes through, is exactly the same. So if the intensity of this light is 100 and what passed through is 100, emission is definitely going to be 0, of course. Right? Make sense? Any questions on this absorption emission issue? Okay, so let's go ahead and move forward. It is that basic. Now here's where we start to get a little bit interesting. So let me make this a little bigger. It's going to take me... The video is going to be a little funky at this point. Hey, that's fun. And the good news, by the way, is here. Now we're going to talk specifically about one of these types of analysis. The first is infrared spectroscopy. Now I know it's difficult for you to see this when you watch this in a video. It's being recorded in fairly high resolution, so you'll be able to see it fairly clearly. But I'll read to you what you're responsible to know just here in class. It says to describe the operating principles of a double beam infrared spectrometer. Now, before I do that, let me be clear about this. You guys, anybody have a microwave in their home? I'm sure you all do. Of course, everybody has a microwave. So a microwave, this is a perfect teaching tool for this process. A microwave works very simply. It uses a specific frequency of electromagnetic radiation that is tuned to be absorbed by molecules of water, specifically the bonds in water. It also works with bonds in fats. If you've ever put something with a lot of grease in the microwave, it heats up very quickly. Whereas if you put things like a plastic dish with nothing in it, you can put it in the microwave and then you can just reach in and grab it. But if that plastic dish was coated with oil and then you put it in, it would be very hot very quickly. And that's because that wavelength of light, that frequency of light is attuned to the bonds in waters, and it also works with some fats. So that's the same principle that infrared spectroscopy is based upon. Infrared light has an effect on bonds similar to that of microwaves. It causes bonds to stretch, to bend, twist. There's all kinds of different descriptions for these movements. Now, you are asked to know some of them specifically. So let me take a moment here. Let me move up here through the curriculum. This is the Chem Guide, so this is online. This is option B. So let me just scroll up to option A. If I had enough time, I'd edit it out of the video, but I'm not going to do it. Okay. So in the Chem Guide here, you can see these compounds. Water. This is similar to a methyl group. This is part of an alkane chain. Sulfur dioxide and carbon dioxide. It says that these are examples of compounds that you'll probably be asked about to explain how this works. And so if you read this bullet point, it says to explain what occurs at the molecular level during the absorption of infrared radiation by molecules, and it uses two descriptors. There's a change in bond polarity, and it talks about vibrations. So the vibrations are the bond stretching, the bendings. The polarity has to do with stretching. So let me go back to that document here. So we'll let's just use sulfur dioxide. We'll use carbon dioxide. It's a little more, it's linear. It's easier for me to draw. So in a molecule of carbon dioxide, when we use some electromagnetic radiation, these bonds can stretch. So think of them as moving further apart from one another. If this was a vertex, they could bend similar to, I don't know, like if you ever drawn those birds when you're a kid, and you draw birds like this. That's the way I used to think of it, actually. So this vertex would be this point, and you could have some bending or flapping effects of this bond. Long story short, the bonds stretch, and because the polarity of this molecule is based upon its shape and position of electrons, so when we change its shape slightly, we're slightly changing its polarity. And those fluctuations in bond length, those fluctuations in polarity are detectable, similar to absorption and emission. Okay? So an infrared spectrometer works primarily on absorption. You shine this light through it, and certain frequencies or certain wavelengths, however you want to phrase it, are absorbed by certain bonds. And so we get certain signals which indicate the presence of a particular chemical group. Does that make sense? Now, in a very, 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 very basic sense, you are required to know how it functions. So I'm going to draw a very, very rough diagram. You can see this bullet point says that a schematic diagram of this is acceptable. So I'll do my best. So here's our light source. Here's your sample. And that light goes through. Now, for reasons that are not actually important, usually it's split. That's why it's called a double beam. Now, these things I'm drawing here are mirrors. Oftentimes, it's called a rotating mirror, or just a mirror. It splits it into two signals. Now, the reason for this is that one of the signals, and it's the same source of radiation, one of the signals will go through a reference sample. That's your control. It's a comparison. It's a calibrated thing where it's like, okay, this is what a baseline is, and your sample, excuse me, this is incorrect. I shouldn't have put the sample there. That's the beauty of this comment. Ignore that. The infrared radiation is split, goes through the sample and the reference, and they are brought back together, and they are detected